evening, everyone. My name is Renu Raman Sahu, and today we will be discussing the fifth assignment of this year and sixth assignment of the previous year. So let us get started with the discussion of question and answers. So here, what the question is asking: an electron beam enters a cross field velocity selector. So what is this cross field velocity selector? Uh, so this cross field velocity selector with magnetic and electric fields have been given. So the cross field velocity selectors means the electric and magnetic field are perpendicular to each other. So if the magnetic field is along this direction, let's say, and the electric field is along this direction, so and this is perpendicular electric field, and the electron beams enters this particular field with some velocity. So electron is entering with some velocity v. So the force, so what this velocity selector will do is so let us see what is the force on this electron. So due to the magnetic field, it is q v cross b. So if you use this formula, Lorentz force is equal to F equal to minus A plus v cross b. So here if you do v cross b, v is along this direction, and the magnetic field is along this direction. So what you get is the force due to the magnetic field will be along this direction. You can think of this v is equal to v naught x cap. This is equal to E naught. So b is equal to v naught y cap and equal to E naught z cap. So if you just put this, what you will see is in this direction you will get the force due to the magnetic field. Force due to the magnetic field, it is just v cross b, and on the opposite direction, so it is just v cross b. So v cross b will be what? So v naught x cap cross b naught y cap. So x cross y is z cap, and so let us see. So F magnetic. So F magnetic is equal to minus E v cross b. So it is just minus E v naught b naught. This v is along x cap and b is along y cap. So x cross y is nothing but minus E v naught b naught. X cross y is z cap. So the magnetic field will be along minus. So it is minus z cap is the direction of this magnetic force. So here it will experience magnetic force along this direction. Okay. F magnetic. So now let us see what is the force due to the electric field. The force due to the electric field will be, it is a force due to the electric field, it is minus A times this electric field magnitude, E, which is nothing but minus E naught z cap. Okay, so it is so we have to, so it is also in, so we have to put this electric field in this direction then. So what we now get is so A is equal to A naught and this is minus z cap. So here in a, because it is minus z cap, the force will cancel out, and so here the force due to the force due to the electric field is along this direction. So if the electric field is arranged electric and magnetic field is arranged along in this direction, then we will be getting some magnetic force along this direction. So I'll just draw it nicely again. So what we will be getting is the magnetic force along this direction has the magnitude of E, B, B, and along this direction we will have the electric force E, E. So at equilibrium, if it wants to go undeflected through this velocity selector, we need to have E, B, B has to be equal to E, E. So what we will have finally is B, so E, the E cancels, and we'll have B is equal to E, and this velocity V or the speed is equal to E by B. Now we have E is equal to, it has been given that 6 into 10 to the power 3 Newton per Coulomb, which is already in SI unit, and B is 2 millitesla. That means 2 into 10 to the power minus 3 Tesla. This means 3 into 10 to the power 6. It will be in SI unit because all the units we have used in SI unit. So it will be meter per second. So this is your correct answer. Now let's go to the next question. Here it is asking the tight binding dispersion relation has been given. So this is the tight binding dispersion relation for electrons in a one-dimensional array, and it has a lattice constant of A and total length is L. Okay, and this E naught, beta, and gamma are constants. So this is a constant, this is a constant, and this is a constant. And K is the wave vector. The effective mass of the electrons is given by. Okay, so the way we define electric mass, effective mass is the energy should be equal to h bar square k square over 2m effective. Okay, and how do we get this thing? We get this by, like, let's say we want to get this m effective. So let us take the derivative of E with respect to k. So dou E by dou k, this will give you nothing but h bar square k over m effective. So if we try to do this derivative again, what we will get is 2 to E by dou k square is equal to h bar square over m effective. Okay, and m effective will be equal to h bar square over 2 to E by dou k square. Okay, so let us do this thing. So we have to find the double derivative of this energy. This energy is usually as a function of k, as shown here. So let us try to do that. A is equal to E naught minus beta minus 2 gamma sine Ka. Okay, if we do first derivative here, so this is a constant, will get 0, this is a constant, will get 0, minus 2 gamma, derivative of sine is what? It is cos Ka into A. We'll do the derivative again. 2 to E by dou k square is equal to minus 2 gamma A square, and it is minus sine Ka minus sine K. So basically it is 2 gamma A square sine Ka. So we have to put this in here. This implies m effective is equal to h bar square over 2 gamma A square sine K. Okay, so it is h bar square over 2 gamma A square sine Ka. So this will be your answer. Okay, so this is how you get the effective mass of the system. Here, so a two-dimensional square lattice is given, and the frequency omega in the long wavelength limit. So we'll understand what this long wavelength limit is. It changes linearly with respect to with respect to k. Then the density of states we have to find, and it is proportional to what? Okay, so the way we do this is, say, uh, so it is a, we have to keep in mind that it is a 2D system. In 2D system we find the number of states, so the number of states is n over v. It is given by, like, we have to find in terms of omega, right? So it will be given by something like this, d omega d omega. This is the number of states per unit volume, and omega, since it is a frequency, it will have like all the states, and this is the number density of states. Okay, and this thing is called density of states. Density of states. So in 2 dimensions what happen, in two dimensions we'll now have, so this is in 3D. Okay, in 2D, so in 2D what will happen, so the number of states will be given by L over 2 pi. Now since it is 2 dimension, we have to do uh, uh, like whole square here, and it is so we are counting actually the number of states. So it is so basically how the states are distributed is like this. So if it is x, it is y, the states are in this plane. So the states are in this particular plane. Okay, and the way we have to count is, so we take a thin strip here which has a radius. So this is actually k in k space. Okay, kx, ky, kz. So we take a thin cell of radius k. Okay, and we span it of thickness dk, and we span it over the entire plane. So it is 2 pi k, which is the circumference of this strip, and dk, and k goes from 0 to infinity. So this is how we count the number of states, and the density of states is defined as, so this L square is nothing but your area. So we can write the number of states is equal to a over 2 pi whole square integral 0 to infinity 2 pi k dk, and we have to multiply a 2 here for spin. Okay, spin. So the number density of states will be given by n over a here for 2D system, is equal to 1 by 2 pi whole square, and this 2 here, and 0 to infinity, this is 2 pi k dk. Now what we require is the some sort of dispersion relation. Okay, so dispersion relation will tell how is the frequency varying as a function of omega. Okay, and what this question is saying is that it changes linearly with respect to wave vector k. So this is linear in k. So let us write that the since it is directly proportional to k, there will be some proportionality constant. Let us call it v. Proportionality constant. Let us call it v. Okay. So now what we have is omega is equal to vk, and v, where v is a constant. So and d omega is equal to v dk, or basically k equal to omega by v, and dk equal to d omega by v. So we just put everything over here. So what we get is 2 over 2 pi whole square 2 pi, and instead of k dk what we'll get, so this is omega d omega by v square. Since v square is a constant, we take it out, and so the density of states is given by g of omega d omega 0 to infinity. Now if we compare these two, what we'll get is g of omega is equal to 2 over 2 pi. So this 2 pi cancels 1 2 pi v square and omega. So what we say this is a constant. So what we get is g omega is directly proportional to omega. Okay. So the density of states of phonons is proportional to this. And what this long wavelength limit it means is that so k is equal to 2 pi by lambda. When lambda increases, k will decrease. So whenever you are asked like long wavelength limit, you have to keep in mind that k will go to 0. Okay. So in the long wavelength limit, k goes to 0. Okay, that is what you have to keep in mind. Here we didn't have to use this information, but it is important, like in some questions you have to put k is equal to 0. Okay, so that's where you might need this like this information, that long wavelength limit means limit k tends to 0, or alternatively limit lambda tends to infinity. Let us go to the next question. The velocity of an electron at the boundary of first Brillouin zone. So usually the Brillouin zone looks like this. So pi by a minus pi by a, and it is something like this. Okay, and here this is first Brillouin zone, and the velocity of an electron. So how we get the velocity? Velocity is nothing but 1 by h bar dou E, and this is E versus K diagram. Okay, dou E by dou K at K is equal to edge of the Brillouin zone. So we have to take a particular edge, either plus pi by or minus pi by A. Okay, so if that's where we want to determine, so you see what is dou E by dou K at that point. So dou E by dou K, that is nothing but here it is, and from the next Brillouin zone, it will, how it will start? It will start again like this. Okay, so basically here the derivative has to be 0. Since this derivative is 0 at this particular point, what we have is the velocity is equal to also 0. So velocity of the electron at the boundary of first Brillouin zone of a crystal, this has to be 0. Now let us go to the next question. So the next question deals with, like, in consider which of the following consider the following statement and choose the correct option. Okay, so let us see all the questions. In a lower dimension, a chain of one atom per unit cell get distorted to form a two atom unit cell. So let us see a chain of one atom per unit cell. So let us say it has that is constant of A. Okay, and if you have followed the tight binding approximation, you will get A is equal to A naught minus 2t cos Ka. Okay, and in the energy band diagram, what you will see is this, something like this. Okay, this is pi by A, and this is minus pi by A. Now what can happen is, usually suppose imagine a case in which some of the electrons, so these atoms are actually not stationary. In reality, this atom should be, the nucleus of this atom should be like vibrating. Okay, and the quantum of those vibrations, those are called phonons. And let's say these two, like during some vibration came together, these two came together, so this can happen. Okay, in that case what will happen, you will have this, then this, then okay, just so this, and this, and the periodicity of this will become how much? The periodicity of this will actually double, so this will be 2a. Okay, and once the periodicity doubles, the type of Brillouin zone that you will get is this. So the edge of the Brillouin zone would be pi over 2a, because now 2a is the periodicity. So what you will get here is, here you will get pi over 2a and minus pi over 2a. What you get is, so here you will see a breaking. Okay. So now you see the energy levels here actually decreased than the earlier energy levels. Okay, and since the energy is decreasing when these two are coming together, we say that this particular configuration is more stable. Means this dimer configuration is more stable than the monomer configuration. So this thing is energetically unstable. So what we get? So we see, and it should spontaneously change to this dimerization, this dimer structure. So what we have is, in lower dimension, particularly in 1D and 2D, this thing is very frequent, happens very frequently. A chain of one atom gets distorted to form a two atom unit cell. So this is true. Okay, and why it is true? Because it gets some advantage in terms of lowering of energy. The electron phonon coupling is responsible for this electron. Okay, so this this band diagram is of the electron. And why this band diagram is changing? Because due to, so what is phonon? Phonon is a quantum of the oscillation of the lattice points of the crystal. So when that atoms vibrate or some phonon modes are there, because of that phonon modes, this will either come together and go further, and that is why this distortion is happening. So this statement is also correct. The final energy depends on whether the atoms moves or right. So it doesn't matter actually, because whether, suppose you consider this 1 2 3 4 5, so either the configuration is this, so there would be something this, or so in this case these are coming together. Okay, or the configuration would be this. So what would happen is, I'll write the other configuration. If it is coming this way, or this way, or this way, you see the final configuration is, so this configuration is same as this configuration. That is why it doesn't matter if the atoms moves right or left, the final energy doesn't depend on that. So this is a wrong statement. Okay, let us look at the last question, the last option. It is extremely difficult to form a regular crystalline lattice in one dimension. So what is this regular crystalline lattice? So a regular crystalline lattice is this. So you have, it is a regular crystalline lattice, but since it is unstable and it has the tendency to dimerize, what we have is, so it is dimerizing because of this is, and this. Okay, so this tendency of dimerization makes this one-dimensional regular crystalline material to be very energetically unstable, and that is why it is true that it is extremely difficult to form rectangular crystalline lattice in one dimension. So this is true. Okay, so your answer is A, B and B. Now let us go to the next question. Which of the following is true for a low dimensional system? So the first option is, so we'll see each of the option and see which is true and which is false. The electronic structure of nanostructures is independent of size. To understand this, if it is true or not, let us look at particle in a box. A particle in a box is nothing but the potential is defined in such that it has infinity and in the length 0 to L it is 0, and here it is infinity. Here this is how the potential is defined. So the type of energy states you get is A is equal to, so the lowest energy state will look like this, the second energy state will look like this, the third energy state will look like this, and so on. So En will be h bar square n square pi square over 2mL square. This you get from quantum mechanics. Or another way to get this is that you think of this as some wavelengths, okay? So here lambda equal to, so lambda by 2 equal to L. So or here like for, I'll just tell the procedure how to get this. So here L is equal to lambda by 2, this is half wavelength. Here L is equal to lambda, which is nothing but 2 lambda by 2. The next excited state will be like this. Here L equal to 3 lambda by 2, and here so here actually I made 5 lambda by 2. So there will be a situation in which there will be 1, 2, 3, 4. So here L equal to 4 lambda by 2. Two wavelengths are there. So basically we can generalize this as L is equal to n lambda by 2 and K is equal to 2 pi by lambda, and A is equal to h bar square K square by 2m. You put K, it is 2 pi by lambda. You can take lambda from here. Lambda is equal to 2L by n. So it is 2L by n. So it is n by L. Now you put this K over here. So this is h bar square by 2m, and K square is n square by square over L square. So E is a function of L, which is the size of the well. Okay, and this quantum well structures, they are these days experimentally realizable. So this statement is the electronic structure of nanostructure is independent of size. That is totally wrong. This is wrong. Okay, the surface to volume ratio decreases as we decrease the size. So let us look at the size of a particle. So the surface to volume ratio that we have to find. How to find the surface to volume ratio? The surface goes as some, imagine let's say a sphere. Okay, a sphere, the surface is 4 pi r square, and the volume is 4 by 3 pi r cube. This goes as some constant over 1 by r. For any geometry, this is for any geometry as goes as r square, and the volume goes as r cube. Okay, where r is the typical length size of the particle, and s by v, that will go as r square by r cube, that is 1 over r. Okay, so what it is saying is, as we decrease the size, so if r is decreased, then s by v should increase, because it is inversely proportional to r. So s by v should increase. So what it is saying is, the surface to volume ratio decrease if as we decrease the size. So this thing is wrong, because it should actually increase. Okay, it should actually increase, but the question is saying that it is decreasing, so it is wrong. The energy spectrum becomes discrete rather than continuous. So when we go to a low dimensional system, imagine that we are in 3-dimensional system. In a 3D system, what is, so just let me know what is the spacing between this kx, ky and kz. it is really very small. Let's say this is kx, ky and kz. The spacing is really small. And what is the gap between the spacing? The gap between the spacing is, this is 2 pi by lx, this is 2 pi by lz, this is 2 pi by ly. Okay. Now imagine that we are going to a low dimensional system. To go to a low dimensional system, what we do is we reduce the dimensionality or dimension of one of the axes. So if we want to go to, so this is in 3D, we want to go to 2D. The way we go to 2D is we'll reduce one of the dimension to really very less quantity, like very small length. So let's say that Lx goes to 0, like it goes to some scale. So if Lx decrease, then the gap between this particle, which is 2 pi by Lx, that will increase. So the type of the kx value that we'll get is, there will be some plate here and it will be filled with the kx points at 0, then there will be next kx points and it will be filled with kx points. Okay, and then there will be next kx points, and this gap is 2 pi by l, 2 pi by l x. Okay, and here the gap should be 2 pi by l y, and this is 2 pi by l z. Okay, now so what we see here is that now these things are in k space. Okay, and if you try to plot the energy band diagram, for each of these you will have a parabolic, because E equal to h bar square k square, so it is kx square plus ky square by 2m plus some this kz value, so h bar square by 2m, and the kz value is given by so this kz is now discrete, kz square, so this is some discrete value. Okay, so what we get is, so as we see in this example, the energy spectrum becomes discrete rather than continuous. Okay, so what we have here is this is also, this is true. Okay, now the Schrodinger equation is no longer valid at extremely small case. So this thing is true, this thing is false, because the Schrodinger equation works even for the very small particles, and it is really applicable over there. So that is valid at small scales as well. Now let us go to the next question. In a Hall effect experiment on an intrinsic semiconductor, which of the following statements are correct? The Hall of voltage is always 0. So here, let us revise what a Hall effect experiment is. In the Hall effect experiment, what you have is, you will have a conductor, it has some cross section area A, and you are trying to inject some current J. That J is equal to I over A, where A is this cross section area, I is the current, and you try to take the voltage along this direction, in the transverse direction. Okay, here we try to measure the voltage in the transverse direction. That voltage is called the Hall voltage. So if this distance is d, then the Hall field is given by the Hall field is given by Vh into t. So Vh over t. Okay. So why it happens? So let us see what is our system. The system is an intrinsic semiconductor. It means equal number of holes and equal number of electrons will be there. Now since so we might intuitively think that okay, since the number of holes and the number of electrons are equal, it can go they can equally distributed themselves on either side, and we'll get different, and we'll get no voltage. But what happens is it also depends on something called the mobility. The mobility of charge carriers mu is defined as what is the drift velocity gained per unit electric field. That is how your mobility is defined. And you can intuitively imagine that lower the mass, more will be the low mass or the low effective mass. Low effective mass is more mobile. Okay. So, so what we have is Hall voltage is always zero. So this is not true. Why it is not true? Because this is not true because the mobility of holes, like holes are heavier. Holes are heavier. But the electrons are light and they can quickly rearrange on the transverse plates of this conductor. And that is why we'll get the major Hall velocity or Hall voltage due to the free electrons rather than the holes. Okay. So it is not true that the Hall voltage is always zero. It is false sometimes. The Hall voltage is negative if the effective mass of holes is larger than those of electrons. It actually doesn't depend on like what you call negative or positive. It just depends on how you are connecting this transverse voltage. Okay, if you reverse the transverse voltage, you will no longer have this voltage here. So you can reverse the polarity of this and you will get a different voltage altogether. So this positive or negative is just a matter of convention of what you want to use. Okay, so this is not a contributing. This is not a correct statement. The Hall coefficient can be used to estimate the carrier concentration of a semiconductor. So this is also not true because the Hall coefficient is dependent on what is the Hall coefficient. It also depends on the mobility of the electrons. Okay, it is not just the carrier concentration which is playing a role. And there are equal number of holes and equal number of electrons in the in the system. So a Hall voltage depends on the mobility of charge carrier. So what we concluded from here is that the Hall coefficient can not be used to determine the charge concentration. So this is wrong. So Hall voltage depends on the mobility of the carriers, and yeah, this thing is true. The Hall voltage is dependent on the mobility of the carriers. So this is true. Now we go to the next question. How many graphene monolayers are contained in 1 nanometer thick graphite sheet? Here it is saying 1 millimeter thick graphite sheet. So how does a graphite sheet look like? Let us just draw from the cross section. So this diameter has been given 0.34 nanometer. Okay, and there is this hexagon, 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 hexagon. So this is from the top view. From the side you will just see this, okay, and the other will be just, since it is graphite, it will be at least like this, okay, and this thickness is at least 0.34 nanometer, and you will be measuring around 1 thick graphite. So the number of layers will be, number of this monolayers will be around 1 divided by 0.34 nanometer, which means 10 to the power minus 3 by 0.34 into 10 to the power minus 9, which is nothing but 1 by 0.34 into 10 to the power 6 layers. So it is 1 by 0.34 into 10 to the power 6 layers, which is 3 into 10 to the power 6 layers approximately. So here it is approximately 3 million, the 3 million monolayers will be there approximately. That is the correct answer. Now what we will do is choose the incorrect statement from the following. So the reactivity increases with decrease in the particle size. Let's say we have some particle. If the size decreases, so surface to volume ratio, which goes as 1 by r, let's say r is the radius. If the r decreases, the surface to volume ratio increases. So what will happen is, and if the particle will decrease, we will have lot of particles for the same volume, lot of particles, and it will have more surface area. Okay. As r decreases, s by v increases, surface to volume ratio is actually increasing. Since the surface to volume ratio is increasing, it will have more surface area, and the reactivity, so for a reaction to happen, the reactants need to see each other, and since there is more surface now, the reactants can see the interface through this surface area. That is why the reactivity actually increases when the particle size will decrease. So this is true. Now the surface to volume ratio increases with reducing the size. So we saw that S by V, it goes as 1 by R, where R is the typical size. Or you can think of a cube as well. For a cube, what is A? A is nothing but 6a square, and volume is A cube. Okay, so S by V, it goes as 6a square over A cube, which is nothing but 6 by A, which goes as 1 over A. Okay, so the surface to volume ratio, if you reduce the size, the surface to volume ratio will increase. So which is a truth statement here. In the semiconductor, the band gap will decrease as the cluster size is decreased. We saw this problem in this one-dimensional harmonic oscillator. In one-dimensional coil. So here we saw that E is nothing but h per square pi square n square over 2ml square. Okay. So the band gap, as the cluster size is decreased, so basically we are decreasing the L. So on decreasing L, E should raise. Okay. So the band gap should actually decrease. It should increase as we. So here what will happen is, we are reducing L. So E should increase. As you decrease the particle size of the particle, the continuous. So E should increase. So what the question is saying is the band gap will decrease, which is a wrong statement. Now what this is saying, the fourth option, As we decrease the size of the particle, the continuous density of state in the band is replaced by a set of discrete energy levels. So this is true as we saw in the previous example that earlier the kx, ky, kz everything was continuous and everything was nearly placed. But now what we can do is on decreasing the dimension along one of the direction, we have now this planes of this kx and ky value. Okay. So what will happen is, as you decrease the size, the continuous density of state in the band is replaced by a set of discrete energy levels. So this is true. And so like the density of states for a 3D, it goes as, for a 3D material, it goes as like this. DOS3D. Okay. And this is energy. Now DOS2D, it goes something like this. Okay. This is DOS2D. And if you still lower the dimension, it will come something like this. Okay, so this is in 1D. Okay, and if you still lower the dimension, it will become just some spikes at the Fourier transform level, at some spikes at the discrete energy barriers. Okay, so it is replaced by a state of set of discrete energy levels. This is also true. So the incorrect option, which is the third option. So now, which of the following represent the correct expression for the velocity dispersion relation and effective mass? So I'll just try to motivate the expression. We know that the energy is given by p square over 2m. If we do a derivative with respect to p, what we will get is p over m. P is nothing but mv over m, which is nothing but v. So v we can write as dE over dp or dE over h over dk. Okay. Or this is in one dimension. If we generalize this to three dimension, so v has to be 1 by h over, and gradient of E. So gradient of E. So E is just a scalar quantity. E as a function of k. What this means is 1 by h bar dou E by dou kx x cap plus y cap dou E by dou y cap ky plus z cap kz. Okay, this is how your velocity will look like. Okay, in an arbitrary direction. And the effective mass, as we discussed earlier, m will be given by h bar square over dou E over dou k square. Okay, this was the first part of this assignment. Now we will go to the other assignments, the week 6 of the previous year. So here there is something called Hund's rule, and we have to find the ground states for the given atoms. And the ground states are represented by something called term symbol. What this term symbol means, so we learn from this filling of these orbitals. So f orbital is half filled. You see this 5s p6. So this is totally filled. The 5s and 5p are totally filled, but f is not totally filled. Okay. How do we know if it is totally filled or not? Like we have, so what are this SPDF, and it will have some angular momentum value, L equal to 0, L equal to 1, L equal to 2, L equal to 3, and the number of magnetic states it will have. So m is equal to, so it will have only 0, just one state, it is -1, 0, 1, -2, -1, 0, 1, 2, it will have minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay. So the number of electrons in each of these 2 electrons can go in. So here ml equal to 0, if 2 electron can go, then so it is totally filled. Okay. If there are like this orbital ml equal to minus 1, it can take 2 electrons, this can take 2 electrons, this can take 2 electrons. Total 2, 2, 2, it can take total 6 electrons. D can take total like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total 10 electrons, then it is full filled. Okay. So F can take total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So totally 14 electrons it can take in total. So anything less than 14, F orbital is partially filled. Okay, so less than 14 in F orbital, it is partially filled. Okay. From here, we will determine for a given species what is the effective spin angular momentum, what is effective orbital angular momentum, and what is the total angular momentum from Hund's rule. Okay. So this we will get from Hund's rule, and the way we represent this term symbol is it is 2s plus 1 L J. Okay. If L is equal to 0, again we will write the same thing. So S P D F for L is equal to 0, 1, 2, 3. Okay. So this is what we are going to do for this species of atoms. So let us look at this species. Here it is 5s2p6. This is totally filled, but it is 4f7. 4f7 is there. So let us see how we apply the Hund's rule to get this, to get the term symbol for that. So the way we do it is, so it is EU plus plus, and I'll write the half filled one for F7. Say since it is F, so what is F? So F for F, L equal to, so S P D F. So this is 0, L is equal to 0, 1, 2, 3. So L equal to 3. So ML is equal to, it will varies from minus 3, minus 2, minus 1, 0, 1, 2, 3. So I'll write here ML. ML values are minus 3, minus 2, minus 1, 0, 1, 2, 3. I'll erase this. Now we have to fill the electrons. The way we fill, so these are different different ml values. Okay, and based on that we'll get what is S and what is L and what is J. Okay. So the way we fill this is, so we have to fill the 7 electrons. So we have to fill each of the spin in separate as long as there are available states. This is just to ensure that electronic repulsion is minimized. So 1, 2, 3, 4, 5, 6, 7. So this is how we fill the 7 electrons. And while filling, the spin has to be in the same direction. Okay. Then after this, if I want to fill something, then I have to start filling in like the opposite spin I have to start filling, because of I have to obey the Pauli exclusion principle. Now what we get is, let us see what is the total spin states. So this is spin half along the same direction, spin half along the same direction. So all this spin will add up. So 1, 2, 3, 4, 5, 6, 7, and it is 7 times half. So the spin state will be 7 by 2. Now what is L? So the way we have to look at L is, so L will be given by what is the sum over this states. So it is minus 3, minus 2, minus 1, plus 0, plus 1, plus 2, plus 3. So it is basically 0. And Hund's rule says that if it is a half filled, then J is equal to L minus S, the magnitude of that. And if it is more than half filled, then J is equal to L plus S and the magnitude of that. So here L is 0 anyway, so L minus S is same as L plus S. So what we get here is, just 7 by 2. Now what would be the term symbol for this? Okay, so we have to calculate 2s plus 1 is what? 2s plus 1 is 2 into 7 by 2 plus 1. This is nothing but your 8. Okay, so term symbol is 2s plus 1 and then L and J. So L is what? L is 0. L is equal to 0 corresponds to S orbital. Okay, so it is 8 S and J is 7 by 2. Okay, so this is your term symbol for this particular species. Okay, so what we got here? 8s 7 by 2. So 8s 7 by 2 is in this option, and sorry, not this option. 8s 7 by 2. So not in this option. So this is wrong. So this is a probable option, this is a probable option, and this is a probable option. Let us do similarly for YB3 plus. Here YB3 plus, we see that it is F13 is there and these two are totally filled. But 4F13 is there. So what we will do is F13 is 13 is less than 14. Okay, so it is partially filled, but it is more than half filled. Okay, so let us try to fill that and determine what is the term symbol for that. Here YB3 plus 4F13. So YB3 plus, this is 4F13. Okay, and here also we will do the similar thing, minus 3, minus 2, minus 1, 0, 1, 2 and 3, and we will try to make the boxes. Now we will try to fill the electrons. So first we have to fill the electrons like this, 1, 2, 3, 4, 5, 6, 7. Then we have 7 and we have 6 more left. 7, 8, 9, 10, 11, 12, 13. Now let us calculate what is S. So S will be what? You see here, this is spin up and spin down. So plus of minus of 0, plus of minus of 0, plus of minus of 0, 0, 0, 0. Only here there is only one free spin. So S is equal to 1 by 2. So 2S plus 1 is nothing but your 2. Okay. What is L? L here you see, so here these two electrons contribute L equal to 0. So these two electrons contribute L equal to minus 1. So minus 1, minus 1, minus 2. And this is plus 1, plus 1, plus 2. So this will cancel the L values of this. This will cancel the L values of this. what you are left with is, like here you have only one plus L value and one minus L value. So one extra minus L value. So L is equal to actually your 3. Okay. Now this is more than half filled. So J is equal to L minus S mod. So it is 3 minus half mod of that. What is 3 minus half? 3 minus half is 6 is 5 by 2. So the term symbol is 2s plus 1 L J. So 2s plus 1 is 2. L is, so here you see L we got 3. L we got 3. What it means is, so S P D F. So it is 0, 1, 2 and 3. So F 3 corresponds to F. So this is 2F J. J, the value of J is 5 by 2. So this is the term symbol. So 2F 5 by 2 is the term symbol for this quantity, for this material. So it is 2F 5 by 2. So let us look at the option where we have 2F 5 by 2. That's all. So what is the here? Well, let us calculate L again. L is equal to minus 3 minus 3. There are 2 minus 3 here and 1 plus 3. So it is minus 3. So what we have to do is L is equal to, okay, minus 3 minus 1 by 2. So it will give me 7 by 2. So what we have is this 2F 7 by 2. Okay, and so our correct option is 2F 7 by 2 is here. Now let us look for this one, 4F8. How do we calculate for that? So we have to do 4F8. So it is minus 3, minus 2, minus 1, 0, 1, 2, 3. And we have 8 electrons to fill. So we'll put 1, 2, 3, 4, 5, 6, 7, 8. So here I have to make this correction. So what we have to do is we have to always take, so this we don't have to take. So what we need is L has to be 3. So L we take the magnitude of whatever the value that we are taking. So L is equal to 3. The Hund's rule will state that according to the Hund's rule, it is more than half filled. Since it is more than half filled, we have to take L plus S. So it is 3 plus 1 by 2. So which is 7 by 2. Okay, so that is why it is 7 by 2. Okay. So here also it is like more than half filled. Here also it is more than half filled. So what we have to do? So we'll find S and we'll find L, and J will be given by L plus S and the magnitude of that. So what is L here? L you can see. So let us find first S. So this will give no contribution to the spin, and we have half and 1, 2, 3, 4, 5, 6. So it is 6 by 2. So S is equal to 3. S is equal to 3. Okay. What is L? L is like this single electron is not contributing anything because L is equal to Ml is equal to 0. So this -1 will cancel with this one. -2 will cancel with this -2. One of the electron here, one of the electron has 3 and one of the electron has -3. But there is an extra electron with -3, and we have to take the magnitude of that. So L is equal to 3. Okay. Now L plus S is what? J equal to 3 plus 3 is equal to 6, and the magnitude of that. Okay, so J has to be 6. So L 3 corresponds to F orbital. So it is just S P D F, and it is like this corresponds to 0, 1, 2 and 3. Now what we have is like we'll calculate this term symbol, which is 2S plus 1 L J. 2S plus 1 is, so from here 2S plus 1 we can calculate 2 into 3 plus 1, which is nothing but your 6 plus 1 7. So it is 7. L is equal to 3, which corresponds to F, so we write it as F. And what is J? J is equal to 6. So what we have to write is 7F6. So this is your third option, 7F6. So this is your third option. So this is correct. Like, I hope you got how to use this Hund's rule. You have to keep in mind that if it is more than half filled, J is equal to L plus S magnitude. For L also you have to take the magnitude of it, and if it is less than half filled, J is equal to L minus S. This is what you have to remember. Now what this question is saying, we have to find something called Landé G factor. So Landé G factor, it is already given, the formula is given. It is 3 by 2 plus S into S plus 1 minus L into L plus 1 over 2J plus 1. Okay, for the ions mentioned in question 1. So for so we already have these things, right? Let us consider for the first one, this particular one. Here L is 7 by S is 7 by 2, L is 0 and J is 7 by 2. Let us use that. For the first ion, which is Eu plus plus, S was 7 by 2, L was 0, J was also 7 by 2. Now G will be equal to 3 by 2 plus, you just put this. So 7 by 2 and 7 by 2 plus 1 is 9 by 2 minus 0 divided by 2. What is J? J is again 7 by 2 into 7 by 2 plus 1 is 9 by 2. If you see here, it is nothing but 3 by 2 plus 1 by 2, and it is 4 by 2, and 4 by 2 is nothing but 2. So Landé G factor for the first ion is 2. So this other so 2 is there in this option and in this option. So let us find for the second ion. For the second ion, L is equal to 3, S is equal to half, and J is equal to 7 by 2. So the second ion, L is equal to L equal to 3, S equal to 1, J is equal to 7. Okay, now you find just G. J is nothing but 3 by 2 plus S is half, and half plus half is half plus 1 is 3 by 2 minus L. What is L? L is 3. 3 plus 1 is 6. 3 plus 1 is 4 divided by 7 by 2. So 2 times J into J plus 1. J plus 1 is 9 by 2. So what we have is 3 by 2 into, so plus 3 minus so we have to calculate this quantity, and if you calculate this quantity it will become 3 by 2 minus, so this is 48 minus 3, so it's 45 over this is 14 into 9. So if we just simplify 3, 3, 4, 3, 4, 4, 4. So this simplifies to 8 over 7, or put here it is 8 by 7. So here G, if you evaluate this quantity, it gives me 8 by 7. Okay, so 8 by 7 is this one. So you already know that this is your solution. Similarly for the third, you know how to calculate S, L and J from Hund's rule. You just have to put the formula and get the answer. Okay, so that is about it. Similarly, you can do the third ion as well. Just for practice, you should do it even if you got the answer. Now, effective for magneton is already given. Again, you know what is J. So effective for effective mu effective. You know what is this Lambda G factor? Lambda G factor you got it from here, this expression. Okay, and you know what is this value of J. J plus 1. Okay. Now again it is totally based on the formula. G, you know, if I want to calculate for the first value, the first ion, for the first ion the G is equal to 2, so I'll put G is equal to 2, and what is J? J is equal to, for the first one, J was equal to 7 by 2. Okay, so I will put 7 by 2, and 7 by 2 plus 1. 7 by 2 plus 1 is 9 by 2. So what I have is square root of 7 into 3, and So this thing will give me around if we just calculate in a calculator, it is 7.94, 7.937 or 7.94. So you already have this value, so this is your correct answer. Okay, so similarly, but the important thing to note is that to calculate, so from Hund's rule, so the important step is you should know how to apply the Hund's rule. From Hund's rule you will get S, L and S, L and J, and from there you will get what is G effective. Okay, this is called Landage effective. Landage effective. And from using this you have mu effective, so G, which is a function of J and S, and times J into J plus 1 and square root of that. So that's all. So it is just simple, put the formula, get the answer. Similarly you can do for the other two ions as well. Now it is asking what is the correct symmetric gauge A vector for a constant magnetic field in y direction. So a magnetic field is given by curl of A, okay? And what we want is this has to be equal to B. So it is a constant magnetic field in y direction, so B is the magnitude, so it should be something like B y cap, okay? And the other components like x and z components, they should be giving me 0. So what we can do, the expression for A is given, these three are the expression for A, and we can try them out if we are getting this value or not. So for the first thing what we can do is I cap, so curl, we basically want to find curl of A. So curl of A will be given by I cap, J cap and K cap, dou x, dou y, dou z, and for the first one you see you have one component along the x cap and one component along z cap. So along the x cap it is bz by 2, so it is bz by 2. Y cap there is no component, and along z it is minus xb by 2, so minus xb by 2. We have to take the determinant of this, and what we will get finally is like for I cap, so I cap we get 0, so I cap it is the partial derivative of y with partial derivative of this with respect to y, which is 0, and this gives me 0. Like for j cap, so it is minus j cap, so j cap, if we have to leave this and this row, partial derivative of minus x b by 2 with respect to x, it is just minus b by 2 minus partial derivative of bz by 2 with respect to z, so which is again b by 2 plus k cap. For k cap what we have to do, so this is 0 minus partial derivative of bz by 2 with respect to y, which is 0, and it is just b j cap or by cap, which is same as this. Okay, so this gives, okay, the first option already gives a constant magnetic field along the y cap. So let us try and see if other options give the same or not. So curl of A for the other one is equal to I cap, K cap, I cap, J cap, K cap, dou x, dou y, dou z, and we have only the y cap component, so it is y and b, y times b. This is 0 and this is 0. We have to take the determinant of that, and what we have here is, you see, if we take this I cap and this is 0, and here partial derivative of yb with respect to dz, which is 0, minus j cap So if you take j cap, it is also coming out to be 0 plus k cap. Again, it is coming out to be 0. Basically, it is giving me 0. So no magnetic field is there at all. So this cannot be your answer. So this has to be wrong. Similarly, let us do for the third one. Third one, it will be what? I cap, j cap, k cap, tau x, tau y, tau z, and it is yb along z cap. So 0, 0, and this is yb here. Let us try to do this. So here, what we will have is I cap and I cap, and this will be partial derivative of yb with respect to y, which is nothing but b, minus j cap, and j cap will be it is giving 0 plus k cap, and k cap also giving 0. So this is a constant magnetic field, but the problem is that it is along the x cap direction. Okay, what is it is asking is I have to get in the y direction. So since I am getting in the x direction, this cannot be the answer. So this is not the answer. Similarly, you can try with the other also. So let us. So it is just a cross product. If you try with this, you will get something different. Okay. So this is also not your option. Let us try to do this problem. Here, what it has been given, the cyclotron frequency of an electron in a magnetic field. So omega c, for an electron in a magnetic field, omega c is given by so it has a contribution. So omega c, the cyclotron frequency, it is given as EB by MC. Okay. Now what we want is, we want to find the strength of the magnetic field and the magnetic length of the electron. So how do we find that? The strength of the magnetic field is given by so first we have to find the magnetic field. So this is the formula we have to use, and Fc is given. We have to put Fc here to get omega c. Omega c will be EB over MC. Okay, and the cyclotron frequency of an electron in a magnetic field and the strength of the magnetic field. So we have to find the strength of the magnetic field. We have to find basically B. B is what? B is equal to omega c MC over A. Okay. So everything is there. Omega c is 2 pi Fc MC over A. Okay, E is the electronic charge, Fc is given in the question, m is the mass of electron, c is the speed of light. You put everything. Okay, 8 meter per second, this is 9.1, 10 to the power minus 31 kg, and Fc is given in the question, it is 2 into 10 to the power 11 hertz, and this is 1.6 into 10 to the power minus 19 coulomb. You put everything, you will get B in Tesla, some number in Tesla, and that you have to convert to Gauss. You have to use this conversion factor. 1 Tesla is equal to Tesla equal to 10,000 Gauss, or it is 10 to the power 4 Gauss. Use this formula and you'll get the value. So, and you'll get the resultant value. Now, what is this LB, magnetic length? So this is important, like you got the formula, this is a straightforward formula. The way we get the magnetic length is, so this is also a straightforward formula. The magnetic length is given by h power c over EB and the square root of that. You use this formula and you will get your relevant answer. So EB, like from here we get E times B is equal to omega C. So EB by C. So EB by C is equal to omega C. So M times omega C. So this is equal to M times omega C. So it is h bar by M times omega C. Okay. And omega C we know that h bar over M. This is 2 pi fc. So everything is there. You just have to put h bar is equal to 1.05 into 10 to the power minus 34 joule second. M is 9.1 into 10 to the power minus 31 kg. And fc is equal to, it is 2 into 10 to the power 11 hertz. You put everything and you will get LB in meter. LB in meter, and you can convert it to angstrom. So you have to use this formula, 1 angstrom equal to 10 to the power minus 10 meter. So whatever you get in meter, you can convert that to angstrom. And what you will get by applying this formula is, you'll get this quantity. Now let us go to the next question. It is asked if the magnetization and the magnetic field intensity of the paramagnet are, so the magnetization, it is given by M, and it is given 37 ampere per meter. Okay, and the magnetic field intensity, it is given by H, and it has been given 10 to the power 4 ampere per meter. So the susceptibility, it is defined as, the magnetic susceptibility is defined as M over H. Okay, and it is, you just have to put the values. So it is 37 over 10 to the power 4, it is 37 into 10 to the power minus 4. And like you remember that, like the units of these two are same, so it is, chi is dimensionless. So you already know that this is your answer. Now let us find what is the flux density. So the flux density, so what is flux density? What is flux? Flux is the magnetic field times some area. Okay, flux density means, so this is flux per unit area, this is your flux density, and this is nothing but your magnetic field. Okay, and so the magnetic field is also called the flux density. Okay, that is nothing but your mu naught M plus H. You have mu naught, you have H, and mu naught is this quantity, and so when you put everything, what you will get is, it is 0.0126 Weber per meter square. Okay, so what is Weber? Weber is the SI unit of flux. Or alternatively, this Weber per meter square is Tesla, like 1 Tesla. Now let us go to the next question. The correct statement about the Larmor Diamagnetism. So let us look at what Larmor Diamagnetism is. So you have some electrons, okay, and it is the so it is first thing we'll note that it is a kind of diamagnetism. For diamagnets, the magnetic susceptibility is actually negative, okay. So uh, so that is the property of the diamagnetism. The whatever the magnetization will be developed, that will be opposing the applied field, opposite of H, okay. So the magnetization developed should be opposite of this, and that is why we call it that is why the susceptibility turns out to be negative, okay, because like uh, chi is equal to m over h, okay. So if m is negative of h, or uh, m is equal to chi h, so if chi is negative, then the magnetization developed in the system is opposite of the applied field. So that is what diamagnetism is. That is why chi has to be negative. So this statement is the value of susceptibility is positive. So this statement is wrong. Okay, it has to be negative. Okay, so all the above statements are correct. So this at least one is wrong. So this has to be wrong. So is the result of it is the result of a partially filled electronic cell. So see, one of the issue is that like uh, if it is partially filled, so it is not the result of a partially filled electronic cell. Usually it happens in a completely filled completely filled cell. And how do we get this is, so this is wrong. The diamagnetic susceptibility is depend on the square of the average radius of the electrons of the atom. So there is a like a kind of a simple heuristic way to get the value of Larmor diamagnetism. So uh, so we have to find the diamagnetic susceptibility. So this susceptibility is what? This is m over h. This is m, and we know that V is equal to mu naught h, or h is equal to V by mu naught. So if we are considering it in some so we have to just put this value, and is equal to, so h is equal to B by mu naught, okay. Now we have to find magnetization. So let us say the system has n number of magnetic dipole moments per unit volume, okay. So n number of magnetic dipole moments per unit volume, and each of them have a magnetic dipole moment of mu, okay. This is magnetic dipole moment. So let us now find this magnetic dipole moment for a single atom, okay. So here we have certain magnetic field B along this direction, and the electrons are circulating this atom in a circular way at some radius r, let's say some average radius r. So what is the magnetic dipole moment is current into pi rho square. Rho square is nothing but your x square plus y square, okay. Now what is I? I is nothing but I over the time. What is the time period of this oscillation? And this is pi rho square. What is the time minus E? Time is equal to 2 pi rho over what is the velocity into pi rho square. The velocity, it can be written as so since it is in a magnetic field, so m v square by rho is equal to e v b. So the magnetic force is actually giving what is the centripetal force. Okay, so from here we'll get the value of v. So v is equal to e b rho over m. Okay, so this rho will cancel this rho, and what we have is mu is equal to minus e, this by cancels this by e by 2. So v is equal to e b rho over m into this rho was already there, it is rho square. Okay, so it is nothing but minus a square b by 2m rho square. Okay, you just put this mu in here. What you get is mu naught over b n by b, and this is minus a square b by 2m rho square. Okay, this b cancels this b. Now you see what is this rho square. Rho square is nothing but, so here rho square equal to some average x square plus y square. If it is some isotropic material, this will be nothing but 2 by, so it is y x square plus y square, x square is equal to y square is equal to z square is equal to 1 by 3 of the average radius square. So it is nothing but, this is 1 by 3 of r square plus 1 by 3 of r square. So basically it is 2 by 3 r square. Okay, so if you just use this thing, so I'll just take it up. Chi is equal to minus mu naught n by v is square by 2m, and this is 2 by 3 r square. Okay, where r is the average radius. So from here you already see that chi is directly proportional to r square. R is the average radius and it is negative. This negative sign says that it is a diamagnet. Okay, so the diamagnetic susceptibility is depend on the square of the average radius of the electron, so which is a true correct statement. Now let us go to the next question. Which of the vector quantity are even under time reversal operation? So okay, we will see how to see which is time reversal is correct, or how do we see this time reversal. So imagine that an electron is stationary. Okay, it will emit some electric field E, some electric field. So this is the electric field, how it is going on. Okay, now the so this field will be still there if you reverse the time. So if you take t to minus t, the field will still be E. So E will be there, it will still be E. Because if you scan on the positive time axis and if you go on the negative time axis, you will just see that the electron is stationary and the field is also stationary. So E is actually even under time reversal system. So you imagine this as you take a video of the electron and its electric field and you play it backwards. Okay, that's how you imagine it. So if you play it in a, if you take a video of the electron, it is stationary, and you play backward that video, it is still stationary. So the electric field will be the same. So you will not get the field is not the electric field is even under the time reversal state. But now let us look at this magnetic field. B. So the magnetic field is generated like one by the rotation of electron. Like suppose this electron is moving in a circle, let's say. So the magnetic field will be generated along this direction. So this is like a for example, there is a current in a loop kind of thing, and in the current, since there is some current, so if you think of this particular loop, if you think of this loop, one electron is moving, and you take the video of that, and when you take try to say this electron is moving this way, so and you use the magnetic field at the center would be the magnetic field will be along this direction. So this is just like since in this loop there is some current, since in this loop there is some current, there will be a magnetic field this way. Now if this is at, let's say, some time t, when you take t to minus t, the electron will start moving in this way, and now the magnetic field will be along this direction. So if it is B, the magnetic field went to minus B. So this is odd under time reversal symmetry. I hope this point is clear. Okay. Now what about the quantity velocity? Okay. So velocity, let's say at some, you take a video of one electron moving in some direction. Okay. Okay. You have some velocity. Now you replay that. So at like during time t, now you play that video backwards. So the electron will follow the same path but in the opposite direction. So V will go to minus V when t goes to minus t. So what we have is velocity is also odd under time reversal symmetry. Okay, odd under the time reversal. Odd under time reversal. So now, see what we learned. This is even. This is odd. So what about the Lorentz force? Lorentz force F is given by minus E plus V cross B. Now this is what? This is even under time reversal symmetry. This is odd under time reversal symmetry, and this is odd under time reversal symmetry. So if you do a time reversal for this, then this E will stay as E, the velocity will go to minus V, and magnetic field will go to minus V because they are odd. Okay, and this minus minus will cancel. So what you get is basically the same expression for F. Okay, so F is also even in time reversal symmetry. I hope this point is clear. So this is even by this logic. And what about A? So what? Which of the following vectors are even under time reversal symmetry? So one of the even quantity is E and F. What about A? Let us see about A. So B is equal to curl of A. Okay, and B is odd, and A is so what we want is we want to reverse the time. Okay, if we reverse the time, so the derivative that we do, so this is like this has the quantities x, So x doesn't change under the time reversal symmetry. So this is x, y or z. So any coordinate system will not change under time reversal symmetry. So the only way we will get this b to be odd is if this is odd. Okay, or you can imagine that if a goes to minus a, this curl of minus a will be minus b. So that is why this a has to be odd. So the answer to the question is like, which of the following vector quantities are even under the time reversal operation? So the even are only the electric field E and the Lorentz force F. So it is just E and F only. Okay. Now what about the other quantities? The magnetization. So the magnetization F, so B is equal to mu naught M. Okay, so this M, so M plus H. This is odd. So since this is odd, this has to be odd and this has to also be odd. Okay, so these two quantities need to be odd under the time reversal. So let us go to the next question. The experimental value of Landau diamagnetic susceptibility of a metal, so x chi Landau, it has been given. Which of the following is false? So diamagnetic, see there is a relation between Landau diamagnetic susceptibility and the Pauli Paramagnetic susceptibility. Okay, and the relation is this. So it is minus 1/3 of Pauli Paramagnetic susceptibility. Okay, so if you just put Landau diamagnetic susceptibility here in this Landau, just put it here 1/3 into 10 to the power minus 6. Okay, so it is minus 1/3 chi Pauli, and this 3 will cancels this 3, minus cancels minus. So Pauli susceptibility is 10 to the power minus 6. Okay. So it is asking which of the value is false. The value of Pauli paramagnetic susceptibility is 10 to the power minus 6, which is true. And here the value of paramagnetic susceptibility 3 into 10 to the power minus 6, which is wrong. The Landau diamagnetism arises due to the orbital electronic motion induced by the applied magnetic field. So this statement is true as well if you go through the derivation of Landau diamagnetism. And the Pauli paramagnetic effect, it arises due to the coupling of electron spins. So this is also true, electron spins with the magnetic field. So this is spin interacting with field, and this is orbital angular moment. So it is basically just the orbital electric motion which is supplied by the field. It is because of that. So this is the true statements. If you go through the theory, you will get to know it. So now we'll look at the last question. Which of the following statement is incorrect according to Hund's rule? The Hund's rule is essential in calculating the term symbol of an atom. So that's what we did in the first question. We calculated something called the term symbol, which is 2s plus 1 L J, and we found S, L, L, S and J from Hund's rule. Okay, and this is called term symbol. So this statement is correct. Due to Pauli exclusion principle, two electrons cannot share the same set of quantum numbers within the same system. This is also true. It is electrons are fermions and they follow the electrons are spin half particles, which is why they are fermions, and fermions follow Pauli exclusion, and that is why they cannot share the same set of numbers. Okay. So now this rule deals with reducing the repulsion between the electrons, which is also true. Why? Because why it is true? Because if you remember that while filling, what we are trying to do, we have -3, -2, -1, 0, 1, 2, 3, and here we try to fill, like if it is a spin up, here we try to spin up, 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 like this is how we wanted to fill. So why it is getting filled in different orbitals? It is just to minimize the repulsion between electrons. So that is why this statement is also true. So the rule does not consider the energy shifts due to spin orbit coupling. This is false. Why it is false? Because like this energy shifts due to the spin orbit coupling. So we you remember that we calculated S, we calculated L, and we calculated J. So this J has the effect of spin orbit coupling. So S, uh, so this is L minus S. If it is half filled, L plus F, it is more than half filled. And then what we used to have was we calculated this effective magnetism, effective magnetism due to G. This is the Landage factor, which is a function of J L S, and it is J into J plus 1. So what this J contains? This J contains the spin orbit coupling already. So it takes into it does take into consideration. So this statement is wrong. So that is all for the today's lecture. Thank you. If you have any questions, you can ask me. Do you have any question or doubt? If not, then we still have 2 minutes time. So